Hello everyone. In this presentation I'll be giving a brief overview of nutrient modeling activities for North Carolina Piedmont reservoirs. In this presentation I'll first summarize the various water quality models that are being developed for Jordan Lake and Falls Lake, and then I'll give an example based on our Jordan Lake water quality modeling here at NC State University. And then I'll talk more about the third-party review that we're performing for the Falls Lake modeling effort. Okay, so let's introduce the current model lineup. I think one way that we can categorize models is based on whether they are statistical or mechanistic. The idea behind a statistical model is that it learns from observed data. In a mechanistic model, on the other hand, we learn from processes. So we try to incorporate all of the relevant processes, that determine water quality and see how the overall system responds. Now, of course, all models really fall somewhere along a spectrum between statistical and mechanistic. For the statistical models, they're typically based on relatively simple, transparent relationships. They often cover longer time periods because that allows them to assimilate more data. And they also provide uncertainty quantification. Mechanistic models, on the other hand, incorporate more processes, obviously. More biophysical rates, more parameters that control those processes, and they also typically model a larger suite of variables, such as different nitrogen species. They also tend to have higher resolution. All right, so they might be run at like a sub-daily time step, and they might have a lake might be divided up into hundreds of different segments. And again, these are just typical characteristics, and there's exceptions to these rules. What I'll do now is I'll show you the models that we have for Falls Lake and for Jordan Lake. So the Falls Lake models I'll put up here, the Jordan Lake models I'll put on the bottom. All right, and for Jordan Lake, we have two models that have been developed recently. We have the NC State hybrid lake model, and I call it a hybrid model because we're actually trying to combine some of the benefits of statistical and mechanistic modeling. And the other model is an EFDC model, which is a very high resolution mechanistic model, and this was developed by Jim Bowen's group at UNC Charlotte. All right, and for Falls Lake, we have three models, all right, that are being developed right now. And so we also have an EFDC model. We have a warmth lake model, which is a somewhat simpler model that can be run more quickly, so it can be used potentially to evaluate different scenarios more efficiently. And then we have a more purely statistical model known as a Bayes network model. Okay, and these are just the lake models. In addition to that, we also have some watershed models that have been developed recently. And here you can see them. For Jordan Lake, we also have what I would call a hybrid watershed model. And then for Falls Lake, we have a warmth watershed model. Okay, so why so many models? Well, I think there's a lot of good reasons to have multiple models, and hopefully I'll be able to convince you. I think different models provide different lines of evidence to support management decisions. All right. As we know, all models are uncertain. They're imperfect representations of reality. All right, so if we can get two models, that have different formulations to give us the same result, that's hopefully going to increase confidence for making management decisions. All right, so for example, if I have a statistical model, where it's data-driven and the data suggest, one outcome, and then I have a mechanistic model that's based more on a large number of mechanistic processes, and it suggests an outcome as well. Hopefully those two outcomes from these two different models are going to agree with each other. All right. Now, if they don't, that's also valuable to have multiple models because they can be used to check each other. All right. And so if the models are giving different answers, then that may indicate an area for improvement. And so modelers can talk to each other and try to understand why their models are different, and if it makes sense, update their models and hopefully get more consistent results. All right, so again, all models are wrong, some are useful, so let's try to build multiple models and see where they agree and where they disagree. Obviously, where they disagree, this essentially identifies an area of uncertainty, and this can be useful because it can help prioritize future data collection and research that might help reduce that uncertainty to get more accurate results in the future. All right, and then finally, different models, just plain and simple, they answer different questions, okay? So some of the questions, that you can answer with a high resolution, three-dimensional model, you might not be able to answer with some of the simpler, more statistical models. Also, for example, in the Bayesian network model, they're hoping to address some of the outcomes in terms of beneficial uses of the lake, which can't be directly addressed using the more mechanistic models. All right, so here's a very quick overview of our NC State hybrid lake model. All right, and so we asked, how important is the sediment layer as a source or sink for nutrients relative to external watershed loads? What are the primary controls on chlorophyll concentrations over time? And how long will it take for the benefits of watershed loading reductions to be fully realized? All right, and so here you can see Jordan Lake. We divided it up into 4 different segments based on constrictions in the reservoir that prevent mixing. And here's, a schematic representation of our model. Here are the 4 different segments. We represent, the nutrients in the water column as well as cycling through the sediment layer. The sediment layer potentially acts as, a long-term storage for nutrients. Okay, and here you can see our model results. So we ran this model over a very long time period, from the creation of the reservoir back in the early 1980s all the way up until present. And you can see it does a pretty good job at capturing both the long-term and the seasonal variability in phosphorus concentrations. All right, and this is for segment 1, the upstream segment, which is most highly impaired. And so that's why I'll focus primarily on that segment. Over this period, what the model indicates is that sediment concentrations in the reservoir, they increased at the beginning when we had these very high phosphorus loading levels, and then over time there's been a gradual downward trend in sediment phosphorus concentrations, which is a good thing. Okay, so once we have a model that we're happy with, we can use it to analyze various future loading scenarios. And so here on the y-axis, I'm focusing on the segment 1 average chlorophyll concentration. And then I have 3 loading scenarios. I have maintaining the status quo loading, shown here in black, and you can see there's very little change in chlorophyll concentrations over time. And then under a 50% nitrogen and phosphorus loading reduction scenario, which would be pretty ambitious, you can see how the chlorophyll concentration drops a little bit at the beginning when that change is first implemented, and then it declines more over time as nutrients are gradually depleted from the sediment layer. And then 100% loading reduction scenario, which isn't realistic from a management perspective, but provides an interesting bounding experiment. Shows, of course, a larger initial reduction in chlorophyll, and then greater changes over the long term. But you can see, that based on our modeling results, that the lake recovery is a long-term process. All right, we can also present results in terms of the probability of exceeding the state chlorophyll criteria of 40 micrograms per liter, considering the various uncertainties in the model. And that's what I'm about to show on a secondary y-axis right here. All right, so here you see this is the probability of exceeding the chlorophyll criterion, and here the dashed lines are showing you that probability under these 3 different scenarios. All right, and now for our third-party review of the Falls Lake modeling. All right, our general goal is to review the Falls Lake watershed and lake models in the context of our recent Jordan Lake modeling research, and also in the context of related scientific literature. To do this, we're participating in model-related work groups and committee meetings hosted by the UNRBA. We're also providing timely real-time input on modeling decisions through memoranda and extra meetings with UNRBA modelers. The 2 primary folks involved in this review are Nathan Hall and myself. Nathan Hall's been involved in a lot of data review and data aggregation for the watershed model. More recently, we've been looking at lake model segmentation, lake model flow balance. I've also been working with UNRBA modelers recently looking at calibrating the model to seasonal trends in nitrate loading. And you can see there's some future activities that I have planned, and I believe Nathan is going to stay heavily involved as well. Okay, so the 2-sentence summary. In this third-party review, university researchers are providing recommendations to the UNRBA Falls Lake modeling effort, considering our experience in Jordan Lake and related scientific literature. The review focuses on nutrient loading and transport and relationships with chlorophyll A. Well, thank you for listening. You'll see a couple links here. One is the link to the Jordan Lake nutrient study, and on the bottom left is a paper that we recently published looking at algal growth limitation in the northern portion of Jordan Lake.